Good morning. So let us now continue what we started yesterday in integrals. So there is one theorem there is one problem I want to talk about. That first, I changed this in the new version. I forgot to change it here. So I want to talk about this integral first. Integral from 0 to 1 sine x over x dx. Okay. And as you see in the question number 16, I am not asking you to find or evaluate. I just want you to show that this integral converges. Okay, so everything is okay. Okay, so what I want to mention, so let me give you some history a little bit about these kinds of problems. So in a Riemann integral theory, if two functions are identical almost everywhere except some finitely many points, there is a theorem that you can study in analysis. It guarantees that if one of them is integrable, the other one is also integrable, and the integrals are all equal. For example, if I give you a function f of x equals to x, and I want to consider the interval from 0 to 1. So let me write it like this. It is f of x equals to x if 0 is less than or equal to x, less than or equal to 1. So is this function integrable or not? The answer is yes, because this function is continuous, for example, on this closed interval, and then we had a theorem that if it is continuous, it is guaranteed to be integrable. But now I just define a new function for you, g of x, and for example, I define it like this. I define it to be 5 if x is 1/3. I define it to be minus 6, for example, if x is 1/2. And then I will define it for x if x is between 0 and 1, but not 1/2 and not 1/3. Yes? So, can you see that this function is almost the same function? It only differs at 2 points. Yes? Because if I ask you what is f of 1/3, the answer is 1/3. But g of 1/3 is defined to be 5. And if I ask you what is f of 1/2, I replace x with 1/2, I get 1/2. But if I ask you what is g of 1/2, the answer according to this definition is minus 6. But if x is somewhere between 0 and 1, but not these two numbers, I define it exactly as before. So if I ask you what is the difference between these two functions are almost identical except at finitely many points, in this case 2 points. Okay, so there is a theorem. Of course, this is calculus. It means that you need to be skillful in calculating things rather than making the ideas very precise. But there is a theorem that guarantees that because if this is integrable, which we know it is because it is continuous, and this function differs by this function only at finitely many points, there is a theorem that guarantees that this function is also integrable, and the value of the integral of this function is the same as this function, even though this function is not continuous as you see here. Yes, please.
Even if we replace it with the type of function that you gave about this rational.
No, I will come back to it. Okay, that's the point. In that case, we have the difference is at infinitely many points. That's exactly the motivation I want to discuss. But at least take this for granted. So if you want to calculate the integral of this, you just calculate the integral of this. By the way, intuitively it is very clear. If you draw the graph of this one, it is a triangle. Yes, so something like that, y equals to x. And it is between 0 and 1. Okay, so if I ask you what is the integral of this function from 0 to 1, this is the area of this triangle. But what happens here, I am just carving out 2 single points and I'm defining it as somewhere else. For example, if x is 1/3, for example, if this is 1/3, I am not defining it to be this one, I am defining it to be, for example, yes, something like this. And then the point is that when I carve out one single line from this region, I am not affecting the area, because the area of one single line is just 0. So that's the idea. So it means that by doing this, I am affecting my function, but I'm not affecting the area. So this means that the area should be the same. So that is the intuitive way of thinking about it. Okay, but the question, usually mathematicians are always thinking, okay, let us try to loosen this idea. So say that, okay, instead of carving out only 2 points, 3 points, finitely many points, what happens if I carve out infinitely many points? What happens then? Okay, so we somehow already know the answer. For example, if you, let me define this function for you, f of x equals to 0, the constant function 0, on the interval between 0 and 1. Yes, this is a constant function 0. Is this function integrable? Yes, because it's continuous, for example. And what is the value? The integral of 0 from 0 to 1 is just 0. So it is not only integrable, but the value is 0. But do you remember we talked about a function, I called it a Dirichlet function. Yes, German mathematician. So it was like this. It was 0 if x does not belong to a set of rational numbers, but it, sorry, the other way around. Yes, that's it. And then 1 if x belongs to the set of rational numbers. So, can I say these two functions are identical? No. Yes, because this function sometimes becomes 1, but this function is always 0. But in how many points they differ? It's not like this case. In this case, these two functions differ exactly at 2 points, finitely many points. But here, this function and the 0 function differ at every rational point. Do you agree? So because if x is a rational number, the value of d is 1, but the value of f is still 0. So they differ at how many points? At infinitely many points. Okay? Now, do you think the previous theorem remains intact? We answered this question, if you remember. The integral of this function is 0. But do you remember what we said about the Dirichlet function integrability? It was not even integrable. Okay? So this example shows that for finitely many, it is a theorem. If you want to see the proof, you can go to a mathematical analysis book. You see that this is proven. But it's immediately you see that if I want to loosen this condition and assume that this is also valid in the case that there are infinitely many points, immediately this example, which is at the right level of your course, immediately tells you, no, this is not correct. Is that clear? But so if you want to have your integration theory that you studied, which is called the Riemann integration theory, there is no way that I can generalize this theorem to contain more differences between these. Okay? But mathematicians also have shown that, of course, this set is infinite. The set of irrational numbers is infinite. The set of rational numbers is also infinite. But it is proven that infinities have different hierarchies. So the number, I would say, the size of the cardinality, that's the correct word, the cardinality of the set of irrational numbers, even though it is infinite, but it is much, much bigger than the cardinality of the rational numbers. So they were asking, can we loosen the conditions of Riemann integrability in a little bit so that we are not losing that much, because a Riemann integral is very fruitful and useful. We want to keep the main essence of Riemann integration the same, but we prefer that this function should also be integrable, because in the majority of cases, this is still 0. So still we want to have the integral of this one to be 0. And that is actually done by Lebesgue, French mathematician, and it is called Lebesgue integration theory, which actually goes back to Riemann integration for this case, but it is more generalized. So if you integrate this in the Riemann sense, the answer is this is not integrable. But if you study higher mathematics and you integrate this in the Lebesgue sense, the answer will be exactly what you expect, and this will be 0. Because we say that this function is 0 in the majority of cases. So let us have. So this is a generalization. So in the Riemann theory, you cannot generalize this theorem. You have to change your integration theory to include this function as an integrable function as well. But now, what I want to mention, this is a little bit of history. This question, this is usually shouldn't be part of your course, but there was one exam question is somehow related to this example. And that's the reason actually I brought this up. So this was an exam question. So I just want to, I will solve that exam question hopefully today. But this is the reason I want to talk about this. So here, the first one is this is very simple. I have just given you an integral. I haven't asked you to evaluate this integral. I'm asking you, do you believe that this integral is convergent or divergent? We have a similar theorem also for this case. In this case, do you see that's an improper integral? Okay, because this function is not defined here. Okay, so the problem is that I want to claim, I'm claiming that this is convergent, but I will define a new function which is called the extension of that. So instead of calling it g, I call it f tilde. And I define it in this way for you. I define it the same function, but if x belongs to 0 and 1, yes, because I cannot say that if x belongs to the closed interval 0 to 1, then you will complain that this is not even defined for 0. But I will define it for 0, okay, in a way that the whole function becomes integrable. And then, for example, I can write it 1 here. Then I am claiming that the function that I have defined for you on the closed interval 0 to 1 is not this function, because this function is not defined at 0, but my function is also defined at 0. This is called an extension of this function, because the value of the function remains almost the same everywhere except at one single point, except at finitely many points, in this case only 1 point. Okay, so that's an extension of this function. But my claim to you is that this extension function is definitely integrable, even though this is not that function, I agree. So can you tell me why this function is integrable? What? No, why this is integrable? Because it is continuous. It is continuous, yes? Because if I ask you what is f of 0, what is f tilde of 0, what do you say? According to my construction, is 1. So that is why I didn't define it any other number, I defined it to be 1. Why? Because now if I ask you what is the limit of f tilde when x goes to 0, what do you say? Because if x goes to 0, it is extremely close to 0, but not 0. So this means that which rule I have to use for f tilde, this rule. And this is a very famous theorem, hopefully you remember that. What's the answer? This is 1. So this means that these two are actually equal. So this means that f tilde is continuous on 0 and 1, closed interval. Be careful, there is no limitations here. So f tilde is continuous on this, and therefore, and consequently, integrable. Okay? So if f tilde is integrable, that remark is a statement of the theorem that the original integral is also integrable, even though I am not presenting any proof for you. Okay? So what I did, I introduced a new function, which is the extension of that function, and because I artifacted it, manufactured it in a way that it is continuous, integrability is guaranteed. And if I ask you what is the difference between this function, which I know is integrable, and the original function, they differ exactly at one single point. So if you accept that theorem, which is not part of your course, and I told you I just want to tell you because of that problem in the exam, then you should agree that this one is also convergent, integral convergent. Okay, so that's it. So I don't know even this is a very famous integral, so you cannot find it exactly, but you can approximate it numerically to any precision, any degree of accuracy that you want. So f tilde is continuous on this one, and since f tilde and f differ at one single point, x equals to 0, sine x over x is also integrable on 0 and 1. So that into the integral converges. Okay? So even some authors, I have seen the books, they don't consider this an improper integral. Because you know the main improper integral of second type is the case that it blows up, it goes to infinity at either here or there, but it doesn't go there. But it is also not a proper Riemann integral. Why? Because in a proper Riemann integral, I start with a function which is defined on closed interval a and b, and for example is bounded. We didn't talk about what happens if f is not defined at some points. So it is not proper in the sense that we started our theory, but it is not that improper because the limit does not go to infinity. Yes? So that's something that I want you to know. Okay, so let us go to the first one, which is similar to the exam question, I will tell you. So if I want to talk about this limit, this integral x ln of x dx, again, this integral, yes please.
Sorry, I didn't understand how that shows that it converges.
No, there is a theorem that I told you that if two functions differ at finitely many points, if one of them is integrable, the other one is integrable. When it is integrable, it means it converges.
But I mean, how will we be expected to show that?
No.
Okay.
No. That's why, even though it's not even in your book, because that's a mathematical analysis. And the reason I told you is because I saw one exam question that somehow is related. And when I checked the answer of the examiner, I realized he's somehow pointing to this theorem. But this is not part of the course. So I'm a little bit confused, okay? But for the time being, what I'm saying is that, do you remember yesterday we solved this integral? This was a real type 2 improper integral. Why? Because close to this point, I have a problem. Not only this ln is not defined, but if I take the limit of my function when x approaches to 0 from above, it was really minus infinity, so it blows up close to 0. So here I have only one problem. The problem is that at 0 my function is not defined, but it does not blow up. Why? If I calculate the limit of x ln of x, x goes to 0 from the right, then this is 0 times infinity, so I will use this trick to calculate the limit. And now it becomes infinity over infinity, so Hobbital's number 2 is applicable. And then I differentiate the numerator, it becomes 1 over x, and the denominator minus 1 over x squared, and x goes to 0 from above. And the answer becomes what? The limit, if I simplify x's and everything, it becomes minus x, x goes to 0 from right, so it becomes 0. So again, the same story happens. Here you remember, I have problem at 0 because 0, the denominator cannot be 0, but when I calculate the limit and send x to 0 from above, I get 1, which is finite. So in that sense, it is not that improper, it's a little bit improper, okay? Everything in quotation marks. So that's the same true here. So there is a big difference between this one and that one. Because here, I don't have this x, and then when I calculate the limit of my function, it becomes really infinity. But here, even though still the function is not defined at 0, but when I calculate the limit, it is 0. So it does not go to infinity. But because it is not defined, we consider this as an improper integral. Again, what is the idea? You can define an extension for this function. If you want to define an extension, I just want to test your understanding. What do you think I will define for my extension this time? You don't need to write this in the exam, but I just want to motivate you. Even in this case, do the limit process. But if you insist to do it a little bit properly, so what is your extension function here? Yes?
You have to define f of 0.
Yeah, so it becomes x ln of x if x is not 0, and 0 because the limit turns out to be 0 if x is 0. Of course, x should also be between 0 and 1. So then this function is continuous, so it is integrable, and it differs by with my function at exactly one single point, so I can just do this logic. But if you want to do that, you just do it, you just pretend that this is really improper integral of type 2, so I will define it as before. I would say that I will take the limit, so from 0 to 1. So for example, I take it c to 1, and this time I send c to 0 from the right, and I do my integral, yes? Okay, so, and then if you don't mind, let us just do it quickly. So if you don't mind, let me take this one to be u. I want to do it by parts. I will take these two together to be dv. Okay, so then what happens? This becomes u is ln of x. This means that du is 1 over x dx. And then dv, I took it to be x dx. Then it means v is 1 over 2x squared. And then do you remember, usually we gave this a name, so let me call it integral, which depends on c, for simplicity of writing. So I would say that IC, do you remember the formula? It is u, this is u dv. The answer is uv, which means this times that, minus, of course from c to 1, minus v du. So integral from c to 1, v is this guy, du is this guy. So if I multiply them, 1/2 goes out, and when I multiply 1x is cancelled, I get this. So this is my IC. If I replace x with 1, ln of 1 is 0. If I replace x with c, it becomes minus 1/2 c squared ln of c. And then this one is what? Minus 1 over 4 x squared from c to 1. So it becomes 1 minus c squared. Am I right? Please check my calculations. So if I put 1, it is 0. If I put c, it becomes that, but there is a minus sign, that's correct. X squared over 2, so it gives me a 1 over 2, so that's correct. Then I put 1 and c subtract. So it seems correct. And now you calculate the limit of I of c when c approaches to 0 from above. Okay, so you don't have any problems here, because if I put 0, it becomes minus of 4. This is not exactly this one. Here I have x ln of x. Here I have one extra one. But that is also possible because I have already done that. In the exam, you have to do it because you probably didn't do it before. But here I can just cheat a little bit. C squared ln of c, I can write it as c times c ln of c. And then this one, I realized, is exactly this one. It is 0. And this one is also 0. So the limit of that one is also 0. Yes?
So in that step, how does it translate to 1 over 4 and then 1 minus c squared?
So this integral is x squared over 2. Then I replace c and 1 and subtract, and this 2 and 2 1 4. Okay, so if I put 0, you'll hopefully agree with me, this becomes 0, so the answer becomes minus 1 over 4. Yes? Does it make sense that the answer is minus? Does it make sense? It is always good about these things. Check. I would say yes, because between 0 and 1, x is positive, but ln of a number less than 1 greater than 0 is negative. So this product is definitely a negative number on this interval, so it makes sense to have a negative number, okay? So hopefully we haven't done anything wrong. So I just want you to understand that this is something good to know. If you don't mind, let me immediately go to the exam question that I was talking about. Might be it was a better idea if I write it, if I had written it there. So this is a little bit complicated question, and see this is exam question number 6. So for each integer n greater than or equal to 1, an is defined in this weird way. We're supposed to calculate the limits of this function. Okay? So let me write this on the board here. So let me start from here at least to save some space. So what is an? A sub n is a sequence defined in this way, 1 over n to the power of 1 over n squared, and then multiplied by 2 over n to the power of 2 over n squared, and then 3 over n to the power of 3 over n squared, and then it continues up to n over n to the power of n over n squared. And usually for these cases, they do not simplify these things, even though they can, so that you can see the pattern. Okay? This is the sequence given to us, and we want to calculate n goes to infinity. So we have to have an idea where to start from, yes? So one thing that you can see is that each term, if n goes to infinity, is 0 to power 0. So 0 to power 0 is an indeterminate form. That's also 0 to the power of 0. And then for the limits of 0 to power 0, do you remember what was the trick we used so that we were able to calculate those limits?
We take the log.
Pardon?
We take the log.
We take the log, or we start with an ln. This is one motivation, that it is a good thing to start with taking ln from both sides. In another perspective, these kinds of limits, do you remember, appeared in the Riemann sum, but of course the name is on it. It was a Riemann sum. It is, even if it is Riemann, it is not a sum, because as you see, it's a product. So another motivation that ln might be a good idea to start from is that I need an operation to change a product to a sum, with the hope that might be I can interpret that sum as a Riemann sum. This is another motivation, but of course, these are just motivations, okay? So this means that in any respect, it is plausible to take ln from both sides. I'm just motivating you, okay? So it was not very strange to take ln. Okay, if you think around these lines that I just mentioned. If I take ln of this function, if ln of an, okay, so let us do it in our head. It will be the ln of this product. But ln of a product is the sum of individual ln's. And each term has an exponent on top. So it means that we have these formulas. We know that ln of a product is ln of x plus ln of y, and we also know that ln of x to some power m, I can move m to the back of the ln. Yes, these are the formulas we have. Okay, so I use both of them in one go to save some time. So what happens? Ln of the first one, this power is moved to the back, so it becomes 1 over n squared, and then I have ln of the first term, which is 1 over n. Plus, the next one is 2 over n squared, ln of 2 over n. 3. And the next one is 3 over n squared, ln of 3 over n. And this continues until the last one, n over n squared, ln of n over n. Okay, and now if you have a little bit of experience, now this sum somehow should look familiar to your eyes, yes? Because you have some kind of 1 over n and you have a sum. If you have learned what I told you before, if you have watched the videos, because some of you, I think, you were not here, I don't know. But it is better to write it as a sigma form, okay? It's easier. So can you help me to write it in the sigma form? So, n squared is always the same, so it remains the same. Then I have ln pattern remains the same. And then here I have n remaining the same. Okay? But this number is 1, 2, 3 up to n. So this should be a k here. And this number is the same, 1, 2, 3 up to n. So I will call it a k. But I will run k from 1 to n. That's in sigma form. Okay? But is this a Riemann sum? If you remember, if I want to have a Riemann sum, what I need 1 over n, so that I can give the role of delta x to it. So let me separate it. So I would write it as sigma. Instead of k over n squared, I write 1 over n with the motivation that I want to have somehow delta x. And then I will copy and paste the rest. So k over n, ln of k over n, and then k goes from 1 to n. Okay? So this is a very similar to a Riemann sum. So I want to somehow give the role of delta x of my Riemann sum to this guy, but I have to guess which function is involved here. And it is not hard to guess. Can you see this? What is the function?
X log x.
X log x. F of x is x log x, ln of x. Why? And then if that is the case, and then what do you take for c sub k? If you remember in the Riemann sum, we talked about that before, I need a ck. So if I want to make this f of ck, okay, so a question mark here, a question mark here. These are the way I'm thinking. I want to engineer this to be f of ck. So I chose f of x to be this, and then I have to choose ck to be k over n. Is this really in the kth interval? In the regular interval? Yes, it is in the kth interval, because in the kth... So let me first of all find a and b. Do you remember what was the trick? I calculate c1, it is 1 over n. I send n to infinity, it becomes 0. This will be my a, interval from a to b. And then do you remember, I calculate the last one. Cn is n over n, which is of course 1. And I send n to infinity, but it will not affect the constant, it remains 1. So this will play the role of my b. So this means that my function should be this function, and my interval should be what? Based on my guess, is 0 and 1. Okay? And then the kth term, do you remember there was a formula a plus k times b minus a over n, but a is 1, a is 0, so if I plug them in, it becomes k over n. So yes, ck is exactly the right endpoint of the kth interval. So it is indeed a Riemann sum. Okay, so if it is indeed a Riemann sum, what can I say? I can say that the answer is the integral of my function. But there is some subtlety, as you see here a little bit. This is your old function that we just did it. Because this is my function, and I realize that this is the Riemann sum of this function, and then on this interval. The point is that, is this function integrable now? You have to say exactly the same words. And it was written in the mention. So you see that this function is defined everywhere from 0 to 1, okay? But it is not defined at 0. If I didn't have that problem, definitely the answer would be the integral of my function within that interval. But here is still the same because they just differ at single point. You have to just mention it a word so that we are doing it. But we have already answered this question, and this question was minus 1 over 4. Okay? This is exactly this integral we calculated. But be careful. This is, I was a little bit careless. Let me clean it. Because this is just the Riemann sum. I want the limit of this function. So the limit of ln of an when n goes to infinity is equal to the limit of the Riemann sum. The limit of the Riemann sum is the integral. Sorry. Yes? And then we calculated this before, and the answer was 1 over 4. But be careful, the question is not asking you what is the limit of ln of an, the question is asking you what is the limit of an itself. So what is the limit of an itself? I can say that the limit of an, that the question mark is demanding, the question is demanding, is equal to the limit e to the power of ln of an, n goes to infinity, because e to power ln of an is the same. And then there is a theorem that because exponential function is continuous, this limit can jump to the exponent. So it becomes e to the power of limit of a n goes to infinity. But this one we just calculated that, but I have to write e to the power of minus 1 over 4. So the answer, if you want to simplify it, is 1 over the 4th root of e. Yes?
And the exponent, it's limit of log of a n, right?
Oh, yes, thank you. Yes, I just told you that this limit can jump up. So if you want to make it precise, this is a Riemann sum, not for this function. You can say that I can extend this function to this extended version that we wrote up there. Yes? This is the important thing. Even this Riemann sum will also be a Riemann sum for the extended version. So if you really want to do it precisely, you would say that, okay, this is not a Riemann sum for this function on this interval because I have a problem. I do the extension. This remains a Riemann sum for the extended one. So it will become integral from 0 to 1 of f extended dx. But we already showed that f extended dx is also minus 1 over 4. So, yeah. So this was the only reason I just brought this up. Might be it is not that very important. This was just one question in the exam. Okay, but now let us continue. The main part is this one, estimating convergence and divergence. It means that usually when an improper integral cannot be evaluated by the second fundamental theorem of calculus because an antiderivative cannot be found or is very hard to find, we may still be able to determine whether the integral converges by comparing it with simple integrals. So that's the idea. And if you don't mind, let me just immediately tell you the theorem. So the theorem, the proof is just 1 or 2 lines, you can just read it yourself. But if I have this scenario, let us say a is a real number, is strictly less than b, but it is less than or equal to infinity. Usually when they write like this in mathematics, it means that you are allowed to take b infinity as well, and you also write minus infinity, because you know that infinity and minus infinity are not numbers. In principle, this is a little bit of sloppy notation, but let us imagine that. And then for every x in the interval from a to b, okay, I know that the function, I have also 2 functions that are continuous. So f and g, continuous. So let me also show you the theorem. If you want, you can read it yourself. Yes, so they are continuous. And then for every x in this interval, f of x is less than or equal to g of x. But this one is also non-negative. So these are the conditions that I have for 2 functions, f and g. Okay? Then there is a theorem that guarantees you this. If you calculate the integral of the bigger function, and you realize that this converges, then what you can conclude from here, you can conclude the integral of the smaller one also converges. So integral of a to b f of x dx converges, and integral of a to b f of x dx is less than or equal to the integral of a to b g of x dx. Okay? So, but you have to be very careful about how to use this theorem. So you have, when you want to use it, you have to justify that you are using the correct version of the theorem. So if the bigger function is convergent, and if the smaller function has to be convergent as well, and the value of this integral of the smaller one is definitely less than or equal to the integral of the bigger function. Okay, and there is another alternative to this one. If this function, if the integral of this one, if integral of a to b f of x dx diverges to infinity, then what do you think I will write here?
G of x also diverges.
Yes, if the smaller one goes to infinity, it forces the bigger one also go to infinity. So it means that the integral of g of x from a to b dx diverges to infinity. But not more than that. For example, be careful about, if this one is divergent, I cannot say anything about f. If it goes to infinity, this smaller one can be finite or can be infinite. It is not guaranteed anything. Okay? So make sure that you are using it. If the bigger one converges to a number, the smaller one is also forced to converge to a number, and that number is smaller than the number for the bigger one. And if the smaller one diverges to infinity, it will also force the bigger one also diverge to infinity. Yes? So for example, let me just write one simple example here. We want to see if this integral, do you see the questions have changed? Consider the following integral, show that I converges, and find an upper bound of its value. They are not asking you to evaluate the integral. Yes? So be careful about this change. So I have one integral from 1 to infinity. I have x e to power minus x squared plus 1 dx. Okay? So hopefully if you have a little bit of experience, you immediately realize that the previous method is not doable here, because this is not possible to integrate. Okay? But we can say that, okay, this function is positive, and if I want to show it is convergent, I have to show that my integrand is less than a function and that function is convergent. The integral of that function is convergent. Okay, so these are very hard problems. These are not that easy to come up with good inequalities. But we have to solve some of them to get some experience. For example, if I write this, do you agree with me so far? Why? Because you see that the lowest value of x is 1. So x itself is positive. X squared plus 1 is positive. E to power minus x squared is positive. So that is not wrong. On this interval, on 1 to infinity, we have this. But do you also agree that this is definitely less than e to power minus x squared?
Yeah.
Why? Because x is positive, and this x squared plus 1 is definitely greater than x. So x over x squared plus 1 is less than 1, so this one is less than this. So this means that if this integral exists on this interval and it converges, this integral also converges because that's a small. But the problem is that we still don't know, because this is one of those functions we cannot calculate directly. Yes?
Can we do x e to the minus
Yes.
x?
So here, can I conclude that this is also true? Do you believe in this one? We have to check. Be careful, by the way. So here, I am working here. So x is greater than or equal to 1. If x is greater than or equal to 1, do you agree that x squared is greater than x? Yes?
Yeah.
And then if I multiply it by minus sign, it becomes minus x squared is less than or equal to minus x. And because e is an increasing function, so e to power minus x squared is less than or equal to e to power minus x. So yes, what I have written here, but in the exam you have to justify this. So you just don't say that it is obvious that this is the case. Okay, especially on the obvious cases you can do, but it is better to prove this one. So now, instead of considering this integral, I will consider this integral on the same interval, yes? And now, if this diverges, unfortunately, whatever I have done is in vain, it is gone, useless. But if I am lucky and I have engineered it in a way that this converges, then I can conclude the smaller one also converge. So what is this integral? Do you think it diverges or converges? So I have to write it as the limit 1 to r, now this is the previous lesson, r to infinity e to power minus x dx. Then it becomes the limit r goes to infinity. Then it becomes e to power minus x. And then I have to run it from 1 to r. Then what happens? This becomes the limit of 1 minus e to power minus r. And then r goes to infinity, and the answer becomes 1. Am I right?
If it's from 1 e
Ah, yes. So this one is what? E to power
1 over.
minus 1, yes? It's 1 over E, thank you very much. Am I right now? Yes, is it correct?
Yeah.
Okay, but now, what can I say? Because the bigger integral, the integral of the bigger function, that's a bad word, the integral of the bigger function converges, and this function, this function, the integral of this function also converges. And if I want to estimate a value for it, the integral of 0 is 0, the integral of this one is 1 over E. So if I called my integral I was not able to find its value, but I was able to estimate that this value should be somewhere between this one. How good is this estimation? We don't know, but that's an estimation. Is that right? So this is the idea of using this theorem. And this is a little bit nasty, you know, it's not that easy. Let me see. There are two important theorems that will help you in this regard. Yes, please.
Why would you not pick x by x squared plus 1 because it's much easier to integrate? Because you know that x e to the negative x squared by x squared
Yeah,
plus
that's
1 has
also,
to be
but
x.
no, that's a good question. This will not work. Let me do that, but that's a very good question.
Because it
So what you are saying is that, let me relax this E.
Yeah.
That's what your question is. Okay, let us do that. That's a good question, and then we will have a break. So your friend is saying actually, is this one true or false? On the other hand, so this is less than or equal to x squared plus 1. This is what you mean.
Yeah.
Is that right, first of all, or not?
Yes, because the max of e to
Yes.
the negative x.
But this will not work. Why? Because if I integrate this on the same interval, that's a very good question, by the way. Okay? If I ask you what is this integral, let us do that. So this becomes a limit r goes to infinity, integral from 1 to r, x squared plus 1 dx. And then this one becomes what? This you learned before. It is 1 over 2 ln of x squared plus 1. But I have to run it from 1 to r. So this becomes the limit of 1 over 2 ln of r squared plus 1 minus 1 over 2 ln of 2. Do you agree? And then r goes to infinity. What's the answer? It's infinity. It means that it was a waste of time. Because the bigger one goes to infinity. It doesn't say anything about the smaller one. So that is the only part. That is the hard part of it. So if you want to prove your integral converges, you have to make it a smaller than a convergent integral. If you make it a smaller than a divergent integral, you cannot conclude anything.
So you would be able to prove that if you did 1 over x squared plus 1 instead, and that happened to diverge, then you know that this one diverges because it's bigger.
Yes, but it doesn't diverge. Because we proved that it converges.
No, I meant
If, yes.
Okay.
Yes. That's exactly the point. Okay, so let us have a break now for 5 minutes and then come back.